Welcome to 6004's course is called Computation Structures. They say that we live in a digital world, and I think they're right, or a world of information and information-driven society. And really, that's the reason we are able to do so is because of digital technologies, our ability to manipulate and transmit and store information accurately and retrieve it quickly and perform billions of computations per second using our laptops, which almost all of you seem to have open in front of you, is because of digital technology, and that's really the topic of this course, sort of soup to nuts. Well, suppose I hired you to sit down and design a computer system that had several billion components in it. And that's pretty much what you have sitting in front of you if you have your laptop open. Now, if you sat down and managed to take out a very, very big piece of paper, and we're going to draw a schematic, and you can say, OK, a billion transistors. I'm going to write down one transistor a second. And when I'm, have them all sketched out, I'm going to do the job. I'll be done with the job. It would take you, many, many, many decades, no sleep, in order to complete that task. So how is it that people do design these systems? And we can get some hints about that by sort of taking one apart virtually. So if we, here's a standard computer system. If we look inside, there's, a little printed circuit board. And already you can see that it's full of a small number of components. There might be 10 or 20 ICs and a modern circuit board inside your laptop or inside your desktop. And if you went and looked, they each have sort of a bunch of little connections. The big chips might have 1,000 connections on them. The little chips only 100 or so. And if you looked at the printed circuit board very carefully, you'd find little copper traces connecting the pins on one of the devices to the pins on the other. So the designer at this level wasn't working with a billion components. The designer was working with a few tens of components. And he had specifications, very high-level specifications about what the components did, and he hooked them up. If we continue sort of our down through little transit down through the computer, if we opened up one of the computer chips and looked inside, we would see something that looked like this. Maybe it's about an inch on a side, the actual silicon die that's inside that package, a little 1,000 connections around the outside. And it would look like a bunch of farm fields viewed from about 10,000 feet. So you look at that and you sort of say, oh, well, I can sort of see there's these rectangular blocks. And if you were particularly good, you could, with your X-ray vision, you could zoom way, way in and see that, in fact, it sort of reminded you of the printed circuit board. There were these components, and they had connections around their perimeter, and then there were little, well, actually still copper wires in the modern processes that connect some of these components to each other. So you're beginning to see there's a sort of fractal-like nature here. We keep finding interconnected blocks. And as we keep going down, we'll discover the same thing. So if I zoom in on one little piece, one of the CPU cores here inside your die, which contains many things besides just a central processing unit, contains memory interfaces and cache memory and graphics units, lots of things that are inside here. If we zoomed in, we might see something that looked like this, which you can sort of say, well, I'm beginning to see a little bit of fine structure. I can sort of get a sense of maybe those stripes across the top are actually a 32-bit bus connecting the, in this case, a very deep register file to the data path of the CPU. And again, the designer has probably worked with, in this case, maybe only 3 or 4 components to wire them up. And if we look at the data path and zoom way in on a piece, I might see something like this, which this is actually a 1-bit register. And now you can sort of say, wow, the dimensions of that thing are maybe let's say about 50 lambda across, where a lambda in the modern world is equal to about 2/10 of a micron. So that's it's getting way below what you could see with actual visual light. I mean, the wavelength of light is a couple hundred microns. So we need fancy electron microscopes to be able to see these sorts of things. And you can all those different colors there represent different materials that have been carefully built onto the integrated circuit substrate to form circuitry. And if we zoomed in on a piece of the circuitry, this is an individual logic gate now. In this case, this is a picture of an inverter. It has a couple voltage controlled switches, one at the top and one at the bottom. This is all stuff we're going to be learning about over the next couple of weeks. But we're going to start our journey by starting with the basics. So we're going to spend a little bit of time today talking about information, and next time we'll talk about how to represent information electrically, and then we're going to start rummaging around our little toolkit of parts and slowly make the same journey, starting with looking at individual metal oxide semiconductor field effect transistors, MOSFETs, and work our way all the way back up. So, long about the 13th week of the course, this picture you'll sort of say, oh, I know pretty much what all those blocks do. So that's the journey we're going to take. So when you look at that picture, what do we see? Well, we certainly saw structure, right? And the key to what we want to do as engineers is hierarchical design. And we try to do that with reusable building blocks. So we have a small set of building blocks that we can hook up in many different ways to perform the function we want. We also saw a bunch of interfaces. Well, it's hard to see an interface, but clearly there was some specification for what the block did and how to use it. That's what an interface is. If you were a software engineer, you'd call it an API. And the reason interfaces are so important is that they allow us to change what's on the inside without affecting how that block gets used. And in fact, one of the keys to sort of the rapid adoption of new technologies in the digital world is that we don't have to re-architect everything in the world because we have a new low-level digital technology. What we do is simply to plug in the new technology but make it obey the old specification. Perhaps it's a little faster, perhaps it dissipates a little bit less power, but in general the functionality was described, and that was what the engineer at the higher level used, was an idea that if I send this particular block an address, I'll get back a piece of data, so that would be a memory. And I can change the technology of the memory without changing that basic rubric of how it gets used. So the interfaces are really a key to the sort of a rapid advancement of technologies that we've been seeing. So what makes a good system design, a good digital design? Well, we're looking for something that, for every dollar that we spend, we get sort of long battery life, high performance. It depends a little bit on what the application is. But we clearly have some metrics that we're going to use to judge the quality of our engineering. We want it to be reliable. These days we expect our computer to work pretty much every place we can, and we can work in temperatures from minus 10 to plus 120, although we have our own sweet spots. But and the phone in your pocket will work over that range too. And that wasn't always the way electronics worked, but it is in the modern world, and we'll get a sense of why that is. And finally, something we want to do is to come up with a basic architecture that will survive over many generations of technological improvements. Okay, so we're going to do this bottom-up journey, and at each level, we're going to work on abstractions. We're going to say, okay, what can we use to make the design at this new level better? So we're going to start with MOSFETs and voltages and currents, but pretty soon, in a week or two, we're not going to be talking about voltages and currents anymore. We're going to be talking about ones and zeros. And after a while, we'll stop talking about ones and zeros and be talking about words and bytes and so forth and so on as we move all the way up. Data structures and stacks and programs and things like that. So, the motto of 6004 could be, spare me the details. What I want to do is sort of each week we'll sort of say, well, that was really interesting, Chris. That's still too much detail for me to do a design of a very complicated system. So what I want to do is to make sure I understand how to specify the behavior and leave the implementation details behind.